The speaker is Yuya Murakami from Tohoku University. The title of his talk is A Proof of a Conjecture by Gukov-Pei-Putrov-Vafa.
Thank you for your introduction. I'd like to thank the organizers for giving me a chance to this wonderful, great conference. Thank you. So today I'd like to talk about a proof of a conjecture by Gukov-Pei-Putrov-Vafa. And Gukov is a speaker in Monday's session. And this talk is based on my preprint in archive. This number appeared in the last week. So to begin with, I introduce the contents of today's talk. In section 1, I'll introduce the previous works of the related topics. In section 2, I'll talk about our main result. And section 3, I'll talk about an asymptotic formula. This formula is the first step to prove our main theorem. And in section 4, I construct a meromorphic function. This is the second step of our proof. And in section 5, I prove the meromorphy of meromorphic function constructed in section 4. This is the final step of our proof of main theorem. And we achieve the proof of the homomorphy by planning operation named by me. This is the operation of weighted trees. Okay, so, but also well known in the low dimensional topology. Okay, so let me start section 1. Okay, so to begin with, I would like to talk motivation of this research. The motivation is to study asymptotics of quantum invariance. And the interesting thing for me is there exists a mysterious, for me, relation to number theory. That is Zagier's quantum invariant. Quantum modular forms introduced by Zagier. I originally studied modular forms, so I'm interested in this relation. Okay, so today we focus on a special type of quantum invariance, that is the Witten-Lichtenstein invariant. WRT invariance. Okay. It is denoted as WRTKM. It is a complex number labeled by positive number K, defined for compact-oriented three-manifold M. Okay. So the one of the most important conjecture to study with WRT invariance is the Witten's conjecture. It states that in the asymptotic of WRT invariance, as K goes to the infinity, Reidemeister torsions and Chern-Simons invariance appeared. And the right-dimensional solutions appeared. This is a Witten's conjecture. So how to prove this conjecture? The first progression is giving by Lorentz and Zagier. They give an idea of proof. In the first step, we should construct a false theta function. It is not theta function, but false theta function. Appeared in Matsaka-san's talk in Tuesday. False theta function Fm tau for M. And in step 2, we should prove WRT invariance for M equals to the limit of Fm tau as tau goes to 1 over k. Okay. Yeah.
Excuse me, is this the SU2 WRT invariant?
Sorry.
Which group are we?
Excuse me. So, this one.
Yeah, which group?
Oh, sorry.
Is it SU2?
No. SU2. So this is SL2 WRT. Thank you very much. And in step 3, so sorry, here I remarked that the false theta function is the function on the upper half plane. So the 1 over k is not to evaluate, but suppose we suppose there exists such a limit. Then in step 3, we should prove the modular transformation property Fm tau, Fm minus 1 over tau equals to tau to some numbers times Fm tau plus some error terms. Sometimes error terms appears. That is why we call false theta function. And finally, we should describe the limit. So by this modular transformation property, by taking limit as tau goes to minus k, then we obtain the asymptotics of WRT invariant because of step 2. In the final step, we should describe the limit along tau goes to minus k of Fm tau. This part here, this part is WRT invariance by step 2. So we need to describe this term. Describe this term as the right-dimensional solutions and Chern-Simons invariance. This is the idea of proof of the Witten's conjecture. So, okay, I'll introduce previous works of a proof of Witten's conjecture. Okay, to begin with, I'll introduce some classes of 3 manifolds. Okay, the first one is the Poincare homology sphere. it is constructed by the -1 surgery of the trefoil. And the second one is Seifert homology spheres. I don't give the definition of this because I don't need its definition in this talk. And the third class is clumped manifolds, clumped Sneer manifolds with negative definite linking matrices. This class also appeared in Gukov's talk. Okay. So we also introduced subclass of third class. 3.1 is the homology spheres. Homology spheres in the third class. Here, homology spheres means the whole homology group vanishes. And we also introduce more subclass 3.1.1. This is lambda H graphs in 3.1. This is the most simple case, not in the second class. Here, I illustrate these classes. The most wide class is the third class, and the 3.1 is in, and 3.1.1 is in, and this is jointly the second class in and the first class in. This is the illustration of these classes. Okay, first, these classes, I'll introduce previous works for these classes. Okay, so step 1 to 4, and the witness conjecture is proved for the first class by Lawrence and Zagier in 99. And for the second class by Hikami in 06. And step 1 is accomplished by Gukov-Pei-Putrov-Vafa in 20. They introduced the homological block. This is a kind of false theta function. Okay, and also appeared in Gukov's talk as the TAT. Okay. So maybe more studies. Step 2 is proved for several cases. Proved for the first class, the second class, secret manifold by Anderson, Mr. God in 2020 and Fuji, Iwaki, Yuya Murakami, and Terashima in 21. There exist more studies. The third class by Mori and me in the last year. Here, Mori is the speaker in today's morning session. The fourth class by, sorry, 3.1.1 class and 3.1 class by me in the last year. So this class, and this class is achieved. So sorry, but this is conditionally. And finally, the most large class, the third class by me in last week. This is today's talk. Okay. So I stopped the section 1 and I will start the section 2. In this section, we talk about the main result. Okay. To begin with, I'll introduce some notations. Let gamma be a plumbed graph that is a tree with weights in rational numbers. And let V is let V is the set of vertices of gamma, and let WV in Q be the weight of each vertex V. And let W, large W, be the symmetric matrix with rational number coefficient, be the linking matrix of gamma, also called the adjacent matrix. And let M gamma be the plumbed manifold for gamma. This is constructed as follows.
Sorry, maybe I should use this now. I'm a bit confused. You said steps 1 through 4 were class 2 by Economy in 06, but then step 2 is proved again by.
It's proved for case 2 is proved for the
Right, so above there, you said steps 1 through 4. Was it-
one is already proved Lorentz idea. And
Second case.
Ah, thank you, thank you. This is for the third case. あ、ここではない。This is third case.
丸2番はステップ1から4全部解かれているのに。
So thank you. So, so this is independent proof by Hikami. So maybe I should write Hikami also, but I omit it. Sorry. Thank you very much. Okay. So let me explain the construction of the Prandtl manifold M gamma, which is also mentioned in today's morning session in Mori-san's talk. For example, let gamma be this graph. And for example, it has weight W and W prime and so on. Then we obtain a link. We obtain a link like this. Like this. And each the trivial knot has rational weight. By regarding these weights as surgery coefficient, by then surgery, we obtain the 3 manifold M gamma. Okay. That is the construction of M gamma. So here, we assume some condition, that is, for any weight is integer, and the adjacent matrix W is negative definite. This assumption is also assumed in Gukov's talk because of define the homological blocks. So by this assumption, our treated class is the third class, the group 3. Okay, so by this assumption, we obtain the homological block for gamma. And here we fix a positive integer k. This Z hat is a Q series, and I give the precious definition later. So under these assumptions, Gukov and Putrov-Vafa conjecture the following equality. That is, WRT invariant of M gamma equals to the simple factor times the limit as Q goes to the root of unity of Z hat, where zeta k is the root of unity exponential 2 pi I over k. This is a conjecture vector. And sorry. So the main theorem of this talk is the above conjecture is true. This is the main theorem. Okay. By this theorem, we can reach the proof of written conjecture. Okay, so let me explain why difficult to prove this conjecture. I think it comes from convergency problem. I'll explain the convergence problem in the simple case. Let theta tau with the usual theta function defined by this infinite series. Here Q is exponential 2 pi I tau. Then we have the modular transformation property that is theta ti equals to 1 over square root t times theta I over t. Then we have square root of t times 1 plus lambda O exponential minus 2 pi t over t as t goes to plus 0. Thus, we have there exists no limit as tau to plus 0 of theta ti. So, a priori, the limit of homological blocks also does not converge like this. But by surprising cancellation of lower factor, Gukov-Pei-Putrov-Vafa conjecture that this limit converges and coincides with WRT invariance. That is a difficult point, I think. So let me explain the idea of this proof. Idea of proof. Okay, so step A, we should develop an asymptotic formula which compares two infinite series which compares to the infinite series. And step B, we should construct a meromorphic function f gamma kt whose Laurent expansion Laurent expansion relates to the asymptotic expansion of homological block. Okay. So in the step C, final step, we should prove that this meromorphic function fk gamma t is holomorphic at t equals to 0, and we should prove f gamma kt k0 equals to WRT invariant. We will prove this by induction on planning. This operation cuts the trees, the leaves of trees. Okay. So next. Here, the most difficult part is step C, because the holomorphy of F gamma corresponds to the existence of limit of the homological blocks. Okay. So let me introduce an asymptotic formula. So to begin with, I'll introduce some notation. Let F and G be the function from R positive to the C, and P be a variable of R positive. Then we give several notation of asymptotic expansions. The first one is due to Poincare. That is, we denote FT sim this infinite series as t goes to +0 if for any integer m greater than or equal to -L, there exists a positive number k and epsilon, and for any positive number t less than epsilon, it calls ft minus the finite sum is greater than or equal to t to m plus 1. And we call this infinite series as the asymptotic expansion of ft. Asymptotic expansion is sometimes diverged to infinite series, but in this definition, I consider only finite sum, so the divergence is not a problem. Okay, so we need more notation. I introduce some notation. Suppose that ft admits some asymptotic expansion, and gt also admits asymptotic expansion. And suppose F and G depends on some data, X, and so on. Then we write xt axim sub x gt as t goes to plus 0, and we call it F dominates G if A0 equals to B0, and for any integer n, there exists number Cn such that Bn equals to An times Cn x. Here we remark that if ft dominates gt and there exists the limit of ft denoted as f0, then we have a limit of gt and it coincides with f0 by definition. Okay, so we need the asymptotic expansion of the convergency of z hat, but we cannot treat directly z hat, so we consider the another meromorphic function f.
Do you require anything on Cn of x? I mean, it seems like you always will have a Cn of x.
Oh, sorry, thank you very much. So it depends only on x number. That is the notation. Okay, so
And what is x?
x is some data. So it is yes.
But what else could it depend on? I don't understand them.
So maybe let me introduce.
If I have a and bn, if they're non-zero, there's always a Cn, no?
Yes. Also, but it's yeah, so we consider sometimes we consider the sequence of fx and gx. So then this definition have meaning. So let me introduce the usage of this notation. We introduce this notation in order to describe this proposition. Let n and k be a positive integer and C be a periodic map with n variables modulo k, and let Px be polynomials with n variables, and let alpha be a vector, and let phi be a Schwartz function. Then we have the asymptotic expansion of this infinite sum n times Pn times f p plus n plus alpha is dominated by the following more simple infinite series of these. This infinite series, the asymptotic expansions of this infinite series is dominated by the following infinite series, that is Cn times Pn times f Pn plus alpha as t goes to plus 0. So this proposition states that, claims that these two, by comparing these two asymptotic expansions of these two infinite series, its differences Cn depends only on f, and this Cnx independence on Cn and Pn and alpha. That is the meaning. And here, sorry. Exponential minus 2 times y plus alpha as t goes to plus 0. Okay. So since this is, we can prove that this is meromorphic function entire. So, but this is sometimes not. So it is simpler than this one. Okay. Oh, but I don't have enough time. So we talk about construction of meromorphic function. I don't give a precise definition, but we define a definition of meromorphic function which dominates the asymptotic expansion of z hat. Okay, so let F gamma kt is the sum of the finite sum of this meromorphic function. Here, Gv is defined as Q minus Q inverse to Q minus degree B. This is the definition. And this form is similar to the WRT invariance. And we can prove that the following asymptotic expansion formula, that is corollary of proposition A is that the homological block is dominated by F gamma kt. Here, the homological block is defined in the Gukov-Pei-Putrov-Vafa talk as some Q series. It is complicated, but it is dominated by this meromorphic function. And its Cnxx is W, the adjacent matrix. Okay, so Thus, our main result follows from the following proposition. Proposition B, WRT invariance equals to some simple factor times the similar sum, finite sum, but does not appear T. And mu runs not KZ. Yeah, mu runs full lattice. It is a difference. Ah, sorry. Sorry. This is the proof and sorry. Follows from so that is F gamma KT is holomorphic at T equals 0 and its value coincides with the asterisk part, that is this part. And finally, I'll talk about how we can prove this proposition B by an induction of planning tree. The planning is the following operation. The planned graph gamma to bracket 1 of gamma is defined as follows. Its vertices consists of a vertex B of V, that is a set of vertices of gamma with its degree is greater than 1. And weight is WV to bracket 1 and does represent to V and degree I equals to 1 times WI universe. This is a plot, the definition of planned graph. Okay, so finally, I would like to talk the idea of proof of proposition B. The shape of gamma is generally very complicated. Maybe like this. The shape of gamma is very complicated, but by planning, this shape is a little simpler because we cut the leaves. So we cut the leaves by scissors. So a little simpler. And by repeating this process, we obtain the 1 or 2 vertex. And for each graph, we need to construct a meromorphic function. This is already constructed by the above. And we need to construct for each point graph. We need, if it is numbered n, then we should construct a meromorphic function. And we need to prove these meromorphic functions are same one. And since this is simple, we can prove proposition B easily. And we obtain the proof. Okay, I'll stop here. Thank you very much.